So we're very happy to welcome Professor Zhaoshan Chang today on Ore Deposits Hub. Zhaoshan is the Charles Fogarty Endowed Chair and Professor in Economic Geology at the Colorado School of Mines in Golden, Colorado. Before working at the Colorado School of Mines, he was the director of the Economic Geology Research Center at James Cook University from 2011 to 2018. And he also worked at the CODES Center for Ore Deposits and Earth Sciences at the University of Tasmania, as well as Washington State University and Peking University, where he completed his PhD in 1997. Zhaoshan has published extensively, and I do mean extensively, on a range of hydrothermal mineral systems, including skarns, porphyry deposits, epithermal deposits, IOCGs, tin tungsten deposits, and even sediment-hosted gold deposits. His projects and those of his students focus on work closely with industry exploration, searching for far field signals, mineralogical discriminators, zonation patterns, geochemical and isotopic indicators that could be used directly as exploration targeting techniques. Zhaoshan currently runs a laser ablation mass spectrometry lab at the Colorado School of Mines, where he supervises students working on ore formation processes and controlling factors of mineralization. Zhaoshan is the International Exchange Lecturer for the Society of Economic Geologists this year. And this week alone, he's given talks to 5 different universities around the world. And we're really thankful that he's chosen to give one of those here on Ore Deposits Hub. So today, Zhaoshan will share some of his expertise concerning skarn deposits, from formation and identification to exploration tools. Zhaoshan, you are up. Thank you.
And thanks to Aaron and Marion for the introduction and for inviting me in the introduction. And thanks to the audience who have been here, and thanks for coming. Today, I'm going to talk about skarns, the zoning patterns, and the controlling factors. And this is a ICEG International Exchange lecture. And if you are not an ICEG member, I strongly encourage you to apply to become a member. There's a lot of benefits to professionals and to students, and it will be good for you for your career. Okay. So while we are talking about skarns, I guess you're here, you already know you're interested in skarns, but I'm still trying to say a little bit more about skarns. There's a lot of skarns worldwide. In my database, there's about 1,600 skarn deposits, and that's the deposits described in the literatures. And if you have worked in the industry, you obviously know there's so many more deposits that hasn't been reported in public literature. So many of them, and in terms of the economic value, skarns is the major source of tungsten and tin in the world. And it's also the significant source of gold, copper, zinc, lead, moly, and iron. And for example, this photo is showing the Antamina open pit in Peru. And it has about 3 billion tons of resources with copper and zinc and silver and moly. And moly is not actually used at the moment. And that was back in 2015. So it must be more larger now. In addition to those metals, there are also silver, boron, beryllium, bismuth, cobalt, fluorine, rare earths, and uranium in skarn deposits. So there's a wide range of metals. And yeah, it's for a company if you have a polymetallic metals deposit, then if one metal price is down, then the other may be up, and it has a little bit of buffer for you. And also skarns may be related to porphyry. There's porphyry related to that skarn deposits. And sometimes depends on the time, and during a certain time, one type or 2 types of deposit may be trending, and it's popular or fashionable. Right now, porphyry is very fashionable, so everybody wants to say this, I have a porphyry deposit. But if you look at Grosberg district, and that's the largest copper gold together deposit in the world. And it's always called a porphyry district. But if you look at 2012, that's Clyde Lice had that paper in the Distal volume. And you look at the numbers, actually, it's about 60% of the copper and 55% of the gold. They are actually in skarns. In other deposits, skarns are smaller. Octadi in PNG is again about 80% of the resources in skarns. Bingham, a big one, about 20%, and Canania, some of them, and Mission and other examples. So we have the skarns typically has high grade and higher grade than porphyry. And if you doing a mining operation, you probably want to mine those ones first to get your cash flow. So it's high grade sweeteners in porphyry deposits. So the importance of skarns. And the skarns, if we have a skarn, and we can have the proximal part and the distal part. And those ones actually can lead to other styles of mineralization. So going to proximal, going more into the intrusion, we can have porphyry style mineralization, and we can also have Grosjean style mineralization, depends on the redox state of the intrusion. And then going further out, then skarns can transition to carbonate replacement deposits, CRDs, carbonate replacement deposits. And further out, we can have kaolin type deposits, or in other places, there's available gold. The gold is not only in the lattice, and so Nevada research. I see Jean is here. Jean is probably will say, "Oh, the gold is visible, so it's not kaolin." So we can call it kaolin-like, but they are similar. They replace carbonate with silicification. Some of the gold is still very fine grained, even it's native gold. So we can have a spectrum of deposits related to skarns. And today we're talking about the zoning patterns. In the zoning patterns, we can have zoning patterns in alteration. We can have zoning patterns in mineralization, in the metals. So those zoning patterns will help you to find out where you are in this system, and whether you are proximal or whether you are distal, and also help you to vector towards the parts. Go to, if you want to find porphyry, you go this direction. If you want to find CRD or kaolin-like mineralization, you go to the other direction. So that's the usage of those zoning patterns. And many times it's also the only way to determine causative intrusion. As in porphyry deposits, in the mineralizing district, you may have multiple intrusions. And which one is the causative intrusion? You really need to look at the zoning pattern and figure out. And some people try to use dating, and I want to, because I run a lab and do dating, and I want to give a caution, because you really need to look at the uncertainties of your dating results. Laser ablation, SPMS, shrimp is typically 1% error, and if you are in a 1 billion year rock district, your error is plus minus 10 million years. So your range is 20 million years. And how long does the ore deposit form? Hydromagmatic related hydrothermal deposit form? At the Octadi example, which is a fairly young 1.3, 1.2 million years, has been shown that one porphyry center with porphyry and skarn, they may only take 50,000 years. And a district is only about 200,000 years. So unless your deposit is very young, or your dating method is very, very high precision, otherwise your dating won't be able to confirm a relationship. It can only deny a relationship or decline a relationship. It can't confirm a genetic relationship. You have to be very careful with this. And it's still based on geology, based on the zoning patterns in skarns. Okay, let's look at the zoning patterns. So in general, we'll start a simple or a typical one, then we'll add in the complexities. So a typical one, if we have an intrusion, we have calcareous wall rock, then we can form endoskarns in the intrusion, this part, and it may be veins, more inside, and along the edge is more pervasive. Then we can have a zone of massive metasomatic skarn, and then further go out, and we can have bleached marble. We say bleached marble is relative to marble. Typically limestones and is dark gray, some of them even black, and occasionally we also have white one, but a lot of them are dark color. And when you change to marble, a lot of them are still returning the color of dark gray to dark gray color. And bleached marble is where the marble become really white. So very simple things to observe in the field, and then you go out to the limestone. So if I'm teaching in the classroom, I will pause and ask a question and wait for you guys to give me an answer. Why do you think limestone, a lot of them are dark color, dark gray to black? It's actually probably related to organic material, and you have marine sediments, there's animals and plants in the ocean, and they die and they together deposited with limestone and form those dark gray color. And that dark gray color, because it's organic carbon, and if you're getting closer to a heat source, some kind of heat, and then the heat will cook up the organic carbon and change them to CO2, and they leave. And if you have higher temperature, there's more of those conversion, and eventually you get rid of all the organic carbon, and then you only have bleached marble. So that's why we have this. Okay, so that's the wall rock. If we have limestone as the wall rock, we have this. If we have calcareous shale, we'll have another scenario. We'll have lots of calc silicate hornfels, and those ones are hard and very fine grained. And if we have alternating bands of limestone and shale, and the contact between the limestone and the shale, we can see reaction scars. And so that's another type of wall rock. And another feature of the hydrothermal signal is fluid escape structures. And those ones can extend not only within the marble, but also into limestone. So they can go far away from the marble front. And that's where you don't even see any skarn minerals. So that's the general pattern. Then you say, oh, sometimes I have a scar, it's quite big. It's a few hundred meters wide, more than 1 kilometer wide sometimes. And if you have that massive scar, you can still be lost. I'm standing on the outcrop of scar. Where do I go? Do I go that direction or that direction? Is the causative intrusion or the all body? So you may say, oh, do you have zoning patterns in the massive scar? Yes, we do. And we will also have some indicators for this. So first, the garnet-paroxysene ratio will decrease away from the causative intrusion. So you're getting away, further away, then more and more paroxysene than garnet. And the garnet color also have a systematic change. It's darker around here, then gets lighter and lighter away towards the marble front. Paroxysene color also change. It's a little bit more subtle, less clear than garnet. Garnet can change from dark red to red brown to brown, yellow, and green. So all sorts of colors. The color change is very obvious. Paroxysene color change is relatively more subtle. They are all green. Here is light green, and here is darker green. If those things you can really do in the field when you do core logging or doing field mapping, and it's easy to use in the field. if you want to do a little bit more lab work, and you can also check the pyroxene and amphibole and look for check the manganese content of the pyroxene and amphibole. They typically increase towards the marble front. And when you are getting closer to the marble front, you can even have manganese minerals like rhodonite and paramangite, bastamite, etc. Those are all manganese minerals. So that's the general zoning pattern for skarns. Okay, next we'll look at some examples. This is a copper skarn, Carfark, basically part of the Bingham, a little bit outside of the porphyry mineralization is the skarn, and there are also skarn inside the igneous complex. But this one is the northwest part, and basically this is the intrusion. We have different wall rocks. We have shale, limestone, sandstone, limestone again, and shale. And mineralization obviously mostly occurs in the limestone. And if we look at garnet pyroxene ratio, you will see here it's garnet much more than pyroxene. Then go here, it's garnet more than pyroxene. Then you go to this zone, it's similar amount of garnet and pyroxene. And then you go further out, there's more pyroxene than garnet. And so that you can see. Sometimes we also have a wollastonite zone at the marble front. Some skarns, yes, some skarns, no, this wollastonite zone. And if we look at the garnet color, we mentioned this is close to the intrusion, red to brown, and go out to brown, then go further out to brown to green, and even further out, yellow to green, and in the wollastonite zone, right next to the marble, there's more amount of garnet, and it's some green and more yellowish color. So the color is getting lighter and lighter away from the intrusion. Another one, this is the copper prospect in Philippines. Its name is called Mexico. This is sometimes the first time I heard about it, I was confused. This is called Mexico skarn in the Philippines. This is not a long skarn, narrow skarn zone from drill hole from 38 meters to 54 meters, only about 16 meters of skarn. And but you still can see the color change. And this is the quartz diorite. This is causative intrusion. You see the garnet is dark red. And then you go further out, it's red brown, then go to further out to brown, then to yellow. And this is light yellow color at the marble front. And so, so you go to many places. I have more examples, but it will show just the same thing. The color has systematic change away from the intrusion. So this is copper. How about zinc? This is the example from zinc skarn. This is Groundhog, Larry Miner's slide and research. And the orange color, that's a seal or a dike, and it's a hypothesis coming off from a major intrusion. The major intrusion may be further west, left side of the picture for a long distance. So by the time we get to this, the end of this hypothesis, it's already lower temperature. And then we can see also still we can see the temperature change or the zoning patterns. The red color is garnet more than pyroxene, and the green color, that's more pyroxene than garnet. And then further out, there's no more garnet, and you start to see bastamite, rhodonite, and those manganese minerals further out. And so that's garnet pyroxene ratio. And when we are at distal location, zinc is typically zinc lead is at distal location, maybe several kilometers away from the causative intrusion. And when we at this distal location, the manganese content in pyroxene will start to be more substantial. So here is maximum JO. JO stands for Zhaoshanite. Zhaoshanite is the manganese end member of pyroxene. So closer manganese is less than 25%, Johansenite is less than 25% in pyroxene, and they go to intermediate zone, they have 25 to 50%, and distal part is more than 50%. Obviously, you go further out and you start to have manganese minerals. So there's more and more manganese. So that's, again, systematic change. Another example, gold skarn, fortitude in Nevada in the United States. And again, a causative intrusion, sometimes you have apotheosis, dike or seal. And if you look at the garnet pyroxene ratio here, 2:1, here 3:1. So in general, it's more garnet than pyroxene around here. And you go to the middle zone, it starts to be 1:3, and there's more pyroxene than garnet. Further out 1:5, and even further out 1:20. So this is only about 5% garnet, so dominated by pyroxene. So garnet pyroxene ratio is there. And because this one is relatively close to the intrusion, the manganese content in the pyroxene is not that high, but still can show subtle changes over distance. So we see here HD, that's Heidelbergite, that's iron end member pyroxene, and in the parentheses, that's JO, Johansenite, manganese end member. So 20, 0%, 0%, 0% manganese, then 4% Johansenite, and 6% Johansenite. It's subtle change, but still increase away from the intrusion. This one shows, it's a small sample, but it can show the zonation. We mentioned dark marble. So further to the right, you will see the dark limestone, and then you have dark marble. And the way, how do we tell it's marble or limestone? It's thumb of rule I use in the field is use your hand lens. If you can see the grain size, I call it marble. Don't see the grain size, that's limestone. So keep it consistent this way. And dark marble, there's still some organic carbon inside this, and you are getting closer to the skarn zone. This is fairly narrow, but it can be fairly useful, being indicative. So this is bleached marble right next to the skarn. And this one actually is mainly to show the wollastonite zone right next to the marble. And you see these big crystals, plated plated and radio aggregates in beautiful crystals. And further to the intrusion, there's garnet skarns. Okay, so we're getting fairly close to the marble front. And further out from the marble front, and the skarns are no longer there, but the hydrothermal system doesn't stop here. And for example, you can see this is in Grosberg district. This is the Big Gaussian skarn, and there's garnet and pyroxene massive, and then this is very sharp contact between the marble. Within the marble, we can still see the green veins coming off the skarn body. And sometimes the green part is fine-grained pyroxene. Sometimes it's chloride. You check it with your hardness, and pyroxene is hard, chloride is soft. This is the example of garnet, and garnet come off as veins into the white marble. And you go further out, that's 50 to 100 meters away from skarn, you definitely run out of garnet and pyroxene, and those black material is black chloride and clay, and sometimes you can see very fine-grained disseminated pyrite in those veins. So 50 to 100 meters away, we can see the veins is still pretty white, and then you go to 200 meters away, and the veins are becoming very narrow, and like stalagmite, very narrow veins. So these are all fluid escape structures, and when you see this, don't let it go and follow up with those type of veins. That's other examples, Yaojialing in China, and you see the convoluted, very fine-grained veins like stalagmite, and that's actually fluid escape textures. And jewel core, you can see also that's so convoluted and narrow veins. And those are all indications of hydrothermal activities somewhere. And sometimes you see those veins, you take a whole rock, you don't see really much anomaly, but you open that vein and you will see iron and manganese oxide coatings of the vein, and you scrap those, and it will give you strong silver and manganese anomalies. And that's, again, good indication of a hydrothermal system around here. So those are all very distal a hydrothermal fluid escape structures to indicate the presence of hydrothermal systems. Likely you're in the limestone, so likely to be skarns. And sometimes you go further out and everything left is just limestone, carbonate and carbonate. And how do I tell there was hydrothermal activity? And this time, if you don't have any other field textures, you can use lab analysis, use carbon oxygen isotopes of carbonate. And so this is our machito in Honduras, and those are skarns, and parallel to the bedding, those are mantles, and perpendicular to the bedding, those are chimneys. And here, that's an example, that's oxygen isotopes, and below that is carbon oxygen isotopes. And sedimentary marine sediments, 20 to 25 per mil, and that's the original sedimentary signature. When you are getting closer to the skarn, you can see the numbers change from 25 to 18, 10, 15, 13, etc. And that shows the signal of hydrothermal activity. So here, if it is just massive rock, carbonated rocks, the halo is 300 to 400 meters in terms of oxygen isotope signal. But if you have a fracture, along that fracture, it can go up to 4 kilometers along faults. So that's another way to tell very, very distal signatures. So as a summary, we can see if we have different types of wall rocks, you will have different zoning pattern or width features and development of skarn and zonings. Shale, we go to getting closer to the intrusion, we change to hornfels and no skarns. And if we have limestone, obviously that's where we have lots of skarns developed. And we talk about garnet pyroxene ratio change, garnet color change, pyroxene color change, etc. And you may or may not have a wollastonite zone. And then you will have a bleached marble zone at the marble front. Then you go to the gray marble and then go to limestone. Then something tiny but important is the fluid escape structures that can go further away from the marble front. If you have different types of wall rocks, you will have different proportions of those products. And if you have calcareous siltstone, you actually have a lot of calc-silicate hornfels. They form during the thermal metamorphic stage. And then it becomes very fine-grained and impermeable. It's actually very difficult to make it into massive hydrothermal skarn. And until you are really, really close to the fluid source, and then you may change a little bit of that. And further out, the scars will only occur as veins cutting through those calc-silicate hornfels. Another scenario is if you have interlayering thin beds of shale and limestone, and then those shale and limestone will have reaction to form reaction scars. Those are metamorphic scars during the thermal metamorphic stage. Then you go closer, then you have bonded scars, and limestone goes to garnet and shale goes to pyroxene. Then going closer, even closer to the intrusion, then you have massive scars around here. The width is, the relative width is also shown on this diagram. Along the edge of the intrusion, we have pervasive endoskarn, and then further inside, it typically occurs as endoskarn veins. So that's the summary of skarns. Okay, that's one part of this. And then you may say, oh, that's nice, Zhaoshan, you presented a very nice zoning pattern. But how come in my deposit, I don't see this obvious zonation? There's more complications. And there are factors affecting the formation of skarns, and it can change those zoning patterns. So based on that simple or typical example, then we add on the more complexities. So the first factor affecting this one is the redox state gradient between magma and wall rock. It's not only the magma, it's not only the wall rock, and it's the gradient between the two. And sometimes people say, oh, I have a oxide skarn, or sometimes, oh, I have a reduced skarn. Well, it depends on, because a skarn zone depends on where you are. It may be different. If you are closer to the intrusion versus you are closer to the wall rock, it may be different. It may be the whole thing is similar. And we'll look at this in detail in the next slide. Then causative intrusion, the volatiles will have impact on skarns and degree of fractionation and redox state. And we don't have time, so I grayed out volatiles, so we won't talk about this today. And I will talk about this when we talk about the metal donations. Wall rock, composition, redox state, permeability, porosity, they all have impacts on the skarns. And today we'll only have time for redox state. Depths of formation, distance from magma, they also have strong effect on skarns, but we'll have to skip it today. We'll look at the redox state gradient. So we have this zoning pattern, but actually to have this zoning pattern, we have assumptions. We have assumptions that the intrusion is oxidizing and the wall rock is reducing. If we have this kind of setting, then we will have this zoning pattern. And the reason for that is the garnet and pyroxene species. So the most common garnet species in skarns are granular and andradite, and they are all calcium. And the difference is here is aluminum and aluminum, and here is iron. And if we have iron here, it's iron 3+. In contrast, if we have pyroxene, the most common ones are diopside, heidelbergite. If you are distal, you have johanssonite. The difference is this site, the B site, magnesium is diopside, and iron is heidelbergite. Manganese will be johanssonite. And you see, we also have iron here, but the iron has different redox state. This is cation 2+. So this is ferrous iron versus ferric iron. So we always say garnet pyroxene, but actually they need to have different species of iron. And if we have 3+ iron, that means it's more oxidized condition, and the iron 2+ will be more reduced condition. And so that explains if we have oxidizing intrusion, and the condition here will be more oxidized, and the iron is more iron occurs at ferric iron, and then you can't form pyroxene, you only form garnet. And you go further out, and you go to the limestone, it is reducing, then the iron mostly occurs as iron 2+. So you cannot form andradite, and you can only, that iron can only go to heidelbergite, and it's a type of pyroxene. So that's why that's more garnet here and more pyroxene here. And that's also explains the pyroxene color. And the more iron you have in pyroxene, the darker the green color. And so that's why it's a light green color here and darker green color close to the marble front. So that's the assumption. Well, is this assumption valid? Well, in most cases, it's especially for copper skarn and moly skarn. And there are lots of studies and show copper and moly have to be related to oxidized magma. So this is right. And carbonate, most of the carbonate is marine sediments, and they are reducing with organic carbon. Organic carbon is very good reductant. So in most cases, it's valid. How about other scenario? If we have nature is never the same, and so we always have exceptions. What happens if we both the magma and the wall rock are reducing? What do you think? If we have everything reducing, then the whole system is reducing. Then all the ion ended up as ion 2 plus. And then you have a skarn dominated by pyroxene. It's very little garnet, if at all. So we have an example here, nickel plate. It's a gold skarn in Hadley district in Canada. And this is the intrusion here. And the dark, the bright red color, that's the Toronto stock. That's the intrusion. And as the economic geologist, when we do mapping, when we see igneous rocks, what do we do first? Well, first you need to take out your magnet and check whether there's magnetite. And if you see black metallic mineral and but it doesn't have magnetism, then it must be eumenite in the intrusion. So if you have eumenite mineral and not magnetite, then it tells you the intrusion is reducing. Something you can do in the field right away. And if you think, oh, let me be more quantitative, and then you can send it out to the assay lab, Acme or ALS, and ask them to do an iron 3 plus and total iron ratio. Titration takes you another $25 to do this. I do an analysis, one sample of 17 elements, $50, and this one analysis is $25. But it's very important. We need to figure it out. If the ratio is 0.4, that's the borderline between oxidized and reducing. And this one is 0.15. Obviously, it's a fairly reducing intrusion. If we have a reducing intrusion, wall rock is typical limestone, so reducing. And the whole system, if you look at this scale bar is 1,000 meters, and this is more than 1 kilometer, almost 2 kilometers of green color. And the green color is pyroxene much more than garnet. So the system is dominated by pyroxene. A little bit of here, that's garnet more than pyroxene. And those garnet will be mostly grossular because of the aluminum or aluminum taken coming off the intrusion. And aluminum has very low solubility, so it doesn't transport for long distance. So they die off very quick. Okay, so that's one end member. How about the other end member? What if we have both the magma and the wall rock are oxidizing? This is the Mexico skarn in the Philippines, and collecting intrusion, coarse diorite, lots of magnetite, fairly oxidizing. And the wall rock is special. It's no longer a limestone. It actually is a conglomerate marble. Maybe there was regional metamorphism and changed everything to bleached marble. Then it tumbled into a valley and formed a conglomerate. So anyway, the Greek, those brown color, that's the clay between the fragments of those marble. And so this is no longer reducing. So oxidizing, not reducing. And what do we have? Well, you ended up with lots of iron 2-3 plus, so you ended up with lots of garnet, not much pyroxene. So that's what we have. We showed that slide showing the color change, but now we're looking at garnet pyroxene ratio. So garnet, and those ones are epidote, so no pyroxene. And here, those are all garnet, a little bit of pyroxene. That's the greenish green color. That's pyroxene, a little bit of pyroxene. Mostly garnet, a little bit of pyroxene here, and mostly garnet, a little bit of pyroxene here. And this one, again, dominated by garnet. So the whole system is dominated by garnet. And if you say, oh, I need to look for my pyroxene to find the end of my skarn, you probably won't find it because the system, the condition is different from the typical example. Okay, so you need to know your intrusion, you need to know your wall rock, so you know your ingredients, and then you can predict your product. Oh, sorry, I thought that slide is about the volatiles. We will skip that. And now we're looking at the effect of wall rocks. And the wall rock, if we have reduced wall rock versus oxidized wall rock, and reduced wall rock will be those carbonaceous. So watch for these two terms. Carbonaceous is rocks containing organic carbon. There's another term calcareous, and that's rocks containing calcite. So this carbonaceous means it's black, containing organic carbon. And this one is oxidized, It's either hematitic, which is red color limestone, or bleached, which is white color. Not really bleached, but they form as white color limestone. So if we have the same intrusion coming into those two sets of the wall rocks, your product will also be different. Say first, we look at the calcitic hornfels. And if the wall rock is calcareous siltstone, we have calcitic hornfels. And that's also the relatively early stage in the thermal metamorphic stage before the hydrothermal skarns form. And in those ones, you see the zone of those pyroxene hornfels is fairly narrow, and there's almost no garnet, very little garnet dominated by pyroxene. And further out, you can also have biotite hornfels, and that's typical for gold skarns. And then if we have oxidized wall rock and your hornfel zone is, you can see it's wider and there's start to have garnet appears. And that's again related to the iron 2+ versus iron 3+ issue. And outside of the garnet zone, then we can have pyroxene hornfels. So much wider plus start to have garnet. If we have limestone, then we'll have hydrothermal skarns. And similarly, again, the width of the skarn is wider in oxidized wall rock than in reduced wall rock. First thing. Second is garnet pyroxene ratio. In oxidized wall rock, you have wider garnet zone and narrower pyroxene zone. Then if you have reduced wall rock, then narrower garnet zone and wider pyroxene zone. And overall, this side is wider. So that's the difference. You think, oh, why do we have this kind of control? Why we have this difference? Remember, that's related to the formation of skarns. And the very basic step of formation of skarn, that's an equation. We have calcite, then we have hydrothermal fluid, bring in the silica. Then we have reaction to form wollastonite. And in this reaction, we have to release what? This reaction will release CO2. So that's a gas you need to release. On the other hand, if your wall rock is reduced and contain organic carbon, sorry, I should write CH4. That's methane. That's mostly organic carbon. This is I just use the carbon. But anyway, so if you have carbon and during thermal metamorphic stage, you already produce lots of CO2. And so you are already flooding the system with CO2. Then when the skarn slightly later to form, you already have CO2 in the system. And then because of this high concentration here, it suppresses the equation or the reaction. So skarn forms much less or slower. Especially depends on your depth, and your depth controls the permeability of the rock. And if you have very shallow depths, lots of fractures, it's probably not a big deal, and CO2 will be released through the fractures. But if you go to deeper locations and your CO2 doesn't really get out that easy, and that's become even more, it become a more serious problem affecting the formation of skarn. Okay, so that's the redox of the wall rock. This one is showing the accommodation and permeability, and we'll skip this. So next, I'm already past 3 minutes. So I will quickly go through the metal zonation. So we talk about zonation in alteration, and now look at the zonation in the metals. And the first thing is, what do we consider? Do we consider all the metals into the zonation, or maybe in nature, those metals don't always occur together? And so we'll use this example, a recent compilation I did about skarns in China, published in the ICG special publication in number 22. Okay, so this is the diagram that's showing 386 skarns in China. And that's one tradition of China is it used to be planned economy and following the Soviet Union pattern. And they traditionally, they didn't care much about the profits. So whatever metals are in the skarn, they will calculate the resources. So in Western country, we'll probably only calculate the one with economic values and skip those minor metals. But in China, everything is calculated. It sounds very silly, but nowadays, actually, it's good for us to look at the metal associations and what's their relationship. Okay, and if we look at, say, let's look at first moly and gold and tin. And it turns out those three metals, they don't occur together very much. So together in this diagram, we have 162 skarns. And between gold and moly, there are only 9 skarns contain both gold and moly. And one of them is a byproduct, it's very small, relatively small amount. And between moly and tin, there's only 4, it's byproducts. Between gold and tin, there's only 2 skarns contains both, and there's only a few tons of gold, and very small. So they really don't occur together. Those 3 elements, metals, they don't occur together. Why is that? What's the reason for this? It's actually related to redox and fractionation of the magma. In terms of redox, tin in nature, you can occur as tin 2+ and tin 4+. Obviously, 4+ will be more oxidized condition. If you have oxidized magma, tin becomes tin 4+. Then in the melt, tin can partition to substitute titanium 4+ and iron 3+. And then it goes into biotite, hornblende, titanite, ilmenite, magnetite, etc. So that means all those tin gets brought down to the bottom of the magma chamber and dispersed into the intrusion. And you don't have any concentrations of tin left in the melt. If you want to really have a tin deposit, you really need to have a reduced condition so that tin occurs at 2+. Then tin doesn't go into any of those minerals and they get concentrated in the residual melt. And later on for your extraction by the magmatic hydrothermal fluid and form deposits. Moly is the opposite. Moly occurs as in nature 4+ and 6+. And if it is oxidized condition, it's 6+, and that's good and doesn't go into anywhere and it gets concentrated. If it is reduced condition, then moly will be 4+. And again, moly 4+ can substitute for titanium 4+, and it goes into biotite and hornblende and titanite, etc. So that's why tin needs to have a reduced intrusion and moly need to have an oxidized intrusion. So they don't occur together because the conditions, the source has to be different. And for between, you say, how about, that's this diagram, this is Larry's compilation redox state, and he used iron 3+ over total iron, that ratio to indicate the redox state of the magma. Overall average is 0.4. That's why we use 0.4 as a threshold. Above that, we call it oxide, below reduced. And you will see copper and moly, that's related to oxide intrusion. And tin and gold only skarns are related to reduced intrusion. Watch out for gold, because gold, we can have gold only skarns and we can have gold copper together with copper skarns. So if we have copper, then the feature follows copper skarn. And if we don't have copper gold only, then that's gold only, is the intrusion has to be reduced. And tungsten can be reduced and oxidized, so the plot is in the middle. So if it is tungsten related to oxide intrusion, you have byproduct, or sometimes can be substantial moly. And if it is together with tin, it's actually a reduced intrusion. It can be both. Zinc and lead, and you have to watch out for this. At the time, when Larry did the compilation, most of them are related to, well, most of them don't have the intrusions identified. and a few of them have intrusion identified is oxide. But nowadays we have many more zinc-lead skarns with the causative intrusion identified. It turns out some of them actually are reduced related to tin skarn. And so this one, zinc lead can be related to oxide magma, can be related to reduced magma. We'll see that a little more later. And you will see here, you say, oh, gold and tin, they both are related to reduced magma. Why not? They don't occur together. That's actually because related to another feature, which is the fractionation of the melt. And tin is typically related to very fractionated magma. See the silica content 73, 74, 75, so very fractionated. Gold only skarns related relatively less fractionated magma. So silica content only about 62, 63. So that's why they don't occur together. So that's the fractionation separate them apart. So last Larry's diagram, and separately, Phil Believin developed this diagram based on deposits in Queensland or in Australia. A similar thing, just using different parameters. For magma fractionation, he used rubidium over strontium ratio, and you higher ratios, it's increasing fractionation. And for redox, he still used iron 3 plus, iron 2 plus, that kind of ratio. So copper, moly related to very fractionated, very oxidized magma, tin reduced magma, tungsten is in the middle. And if you have tungsten moly, that's more oxide. It should be more oxide, and tungsten tin is more reduced. Yeah. And fractionation, moly and tungsten, moly and tin, very fractionated, tungsten, moderate fractionation to fractionated, and copper and gold and iron, they are all related to less fractionated. It doesn't have gold here. The gold only skarn should stay here at this location. Okay, so that's why the three metals don't occur together. How about this one? Copper and tungsten and tin. One of the obvious things you will notice is we always say tungsten tin, but actually there are very few skarns contain both tungsten and tin. It's either tungsten or tin. So over here, that's 180 skarns, only 10 skarns contain both. And still, most of them are dominated by one. There's only two actually, well, that's at least maybe three, has similar economic values of tungsten and tin. So they're very rare actually. So watch out for this. You shouldn't expect to see both economic tungsten and tin in the same deposit. Tungsten and copper, tin and copper, it's not that much association, only 13 out of 184. And so again, that's probably because tin is related to reduced magma and copper related to oxidized magma. Copper and tungsten actually has moderate association. So along this axis, there's many ones, that's because tungsten is moderate fractionation, moderate oxidation, redox. It can be related to fairly oxidized magma too. So that's why the connection between tungsten and copper. It actually, long time ago, 1998, Rainer Newbury in his summary, he already noticed this, and that's what he wrote. Classic tungsten skarns, even the reduced one associated with S-type granite, contains little tin. So not very much association between tungsten and tin. Okay, the next one, let's look at copper and gold and moly. That's the three metals actually, same three metals for porphyry, copper porphyry deposits. And the pattern is similar. So we can have copper gold, very strong association, copper moly, strong association, but between gold and moly, really not much association. You can have copper gold moly, but almost no gold moly skarns or even porphyry. So like we talk about, gold is less fractionated and reduced, and this one is oxidized and very fractionated. So that's two opposite direction. So that's why they don't occur together. Yeah, copper and gold, those gold together, that will be the gold together with not the gold only skarn. It's the gold as sometimes we say byproduct of gold, but copper, but sometimes the gold is more important than copper. So it can be both ways. Okay. We took look at both moly and copper. Both are related to oxidized magma, but they may still be a subtle difference. And this is the using the serum 4, serum 3 in zircon to characterize the redox state of magma. The green color, those dots are porphyry moly and skarn moly, and those yellow ones are porphyry copper deposits. And you can see actually porphyry copper have slightly higher redox state than porphyry moly and skarn moly. So there's a little bit of difference. Then we look at tungsten moly, and this one is actually shows very strong association. In fact, in the number one, the first, the largest, the fifth largest, and the 9th largest moly barren skarn, moly actually is subordinate to tungsten, so they occur together. And tungsten is the major metal, and moly is the subordinate metal, but they're still way bigger than most of the porphyry moly deposits outside of China. Yeah, the first one, moly skarn, is part of a porphyry moly system. It's the skarn itself is bigger than Climax in Colorado, in our backyard. Okay, so that's moly and tungsten. They're both related to fractionated and oxidated magma, so they can occur together very much. Zinc lead, and watch out for zinc lead. Zinc lead can have strong fractionation association with iron, which is indicates it's oxidized magma, and also with copper. And also a lot of zinc lead is related to associated with tin, that's reduced magma. So zinc lead is not picky. It can come from both reduced and oxidized magma. And so in fact, the largest zinc lead skarns, zinc lead metals actually are in tin skarns in China. I'll show this diagram. Top 10 largest zinc lead skarns in China. Number 1, Gejiu, is actually a tin skarn. Number 2, Dachang, another tin skarn. Number 3, Dulong, another tin skarn. So it can be related to reduced magma. Basically, zinc lead can be related to any other metals. Iron is another one. Iron, you can see iron associated with gold, copper, yeah, not much tungsten, but with moly and with zinc lead too. So iron can be related to many types of other skarns. And this is not surprising because when you form skarns, garnet pyroxene, they can contain, the iron species contain more than 20% iron, and chloride 20 to 30% iron. And you start with the limestone with no iron at all. So how do we get the iron? It has to come out of the magma. And you need to have lots of iron to form the skarns. And the excessive iron will eventually go to form magnetite. And in fact, many of those gold iron skarn, even some of them related to tin, regolith in North Queensland, and also in some deposit in China. There's lots of magnetite. Mount Lindsay in Tasmania, also lots of magnetite. In terms of volume, the magnetite is much more than the sulfides. But the economic part is in the sulfide, so iron doesn't get mentioned. So that's one thing you have to really watch out, because some people, when they see there's iron, and no matter, maybe with copper, maybe with gold, maybe other things, then they will say, oh, this is IOCG. So watch out for this. A lot of them are skarns. You have to watch out for this. This is very typical in skarns, large volume of magnetite. Okay, so as a summary, the metal zonation association, we can separate them into actually 4 sets. If there's oxides moderate to strong fractionation, we have moly, tungsten, maybe copper, a little bit of copper, then zinc lead. And oxides weak to moderate fractionation, then we have iron and copper, and then gold and zinc lead. Reduced and strong fractionation is dominated by tin, but you still can have some iron and copper sometimes, and maybe some tungsten is actually okay or typical. Zinc lead, distal part. If it is reduced and weakly to moderately fractionation, you will have gold only skarn close to the intrusion and zinc lead away from the intrusion. And also zinc, actually gold can also be distal. Yeah. So we figure out the association. So we can't put all the metals into one zoning pattern. Then we look at the zoning pattern. Okay, zoning pattern. The common things, zinc lead being distal is very well known. Everybody knows zinc lead is distal. And many people say, oh, I have zinc lead. If I go further exploration, getting closer to the intrusion, I should have copper. I want to find my copper and maybe gold also. But are you going to really have always have copper? Watch out for this, because we already shown zinc lead can also be related to tin. And that's Gezhou deposit 3 million tons of tin, 5 million tons of copper, 28 million tons of zinc lead. So the largest zinc lead actually is related to tin. You may find copper, you may find tin. And how do we know? And you have to look at the mineralogy and look at this is getting towards the oxide source or getting toward the reduced source. If the oxide source, yes, copper. And if it is reduced source, you probably get tin mineralization. Zinc lead is being distal is well known, but actually there are also other mineralization can also be distal. This is an example of distal tungsten skarn. And see, this is the boundary between dirty limestone and shale, and this tungsten mineralization occurs at the boundary between the two. The causative intrusion hasn't been found yet, so this is distal mineralization. This one may not be that big, but we have the largest tungsten deposit in the world. This is Zhaoshan with 2.7 million tons of tungsten. This is not ore, this is metal. So 2.7 million tons of copper, tungsten metal. And it also has copper, and it actually started mining as small open pit of copper. And you look at the intrusion here, that's another thing to watch out. In the early days summary by Larry and Larry Maynard and Rainer Newbury, they probably use examples in North America, and they say tungsten is mostly related to deep intrusions, very large batteries. But actually in China, the recent years discovery found actually those deposits are much bigger than the America examples, and they are also related to shallow intrusion. You see the intrusion actually terminate below the surface. So another revision of traditional wisdom is that if you want to find big tungsten skarns, you need to go into the shallow intrusions. Look at the shallow intrusion. And so the mineralization here, the pink is tungsten ore body, and the green, that's tungsten. Sorry, the pink is tungsten, the green is copper. And you can see when you go further away from the causative intrusion, you only have copper left. And the copper actually is distal, they're not proximal. So we have distal copper veins as a copper tungsten system. Okay. Other metals at distal location, we can have distal tin, and we can have distal moly and distal gold. So those ones can also be distal. So watch out for this. And the metal zonation, that's the top 10 skarns of each type. And summarized in this table, you probably won't be able to see that detail, but in summary, we can summarize those into, again, four sets, depends on the association. So if we have reduced intrusion, strongly fractionated, the intrusion, we're gonna have Grosjean alteration and mineralization, tin plus minus tungsten. And proximal skarn will have tin plus minus copper plus minus iron, maybe small amount of copper. And in distal, we can have distal tin veins. And then far distal, even further away, the veins, the mantles or chimneys becomes zinc lead. So that's this set. If we have oxidized weakly to moderate fractionation, then in the intrusion, we can have porphyry and or inoskarn type alteration with mineralization of moly and or copper. And typically moly is concentrated in the intrusion and very narrowly outside of the intrusion, very close to the intrusion. Then proximal skarn, we can have copper and or iron and plus minus gold, plus minus moly. Then go further out, we can have distal copper as veins, and then far distal, further out, we can have zinc lead plus minus gold. If we have the third set, oxide intrusion strongly fractionated, and then we can have porphyry moly and not much copper, and we can also have Grosjean tungsten, the oxide magma fractionated and can be tungsten moly. So proximal skarn, we can have moly and or tungsten and plus minus iron plus minus copper because it's oxidized. And further out, we can have moly or tungsten as distal veins plus minus copper. So far, not zinc lead yet. And reduce intrusion weakly to moderate fractionation. In China, we don't have examples, but outside of China, like nickel plate in Canada, we can have proximal gold skarn mineralization. That proximal skarn gold mineralization. Intrusion, I need to do more work to figure out the intrusion. Maybe that'll be the traditional intrusion related gold, but maybe not. And because Rich Goldfarb says the intrusion related gold, and a lot of them are related to metamorphic process. But anyway, but you go further out in distal part, we can have zinc, lead, and gold. And that's the example, Caijiayin in China. And that's this type of skarn. And you will notice gold is everywhere. It can be proximal, it can be distal, it can be related to oxidized magma, it can be related to reduced magma. And so it's just everywhere you can have gold. Probably related to the versatility of the gold transportation. High temperature, oxidized magma, more salinity than gold transported as chlorine complex. And reduced condition, you have bisulfite complex transportation of gold. So they can go all sorts of environment. The metal donation part is summarized in the paper, and that's in the book ICG Special Publication number 22. And it has lots of 1,300 deposits reported in this book, many type of deposits, including skarns. And if you want to order, and that's where you can get order. As a final remark, and no one metal zoning patterns can fit all skarns. You have to watch out. You can't expect everything in one system. Second is like the distal zinc lead skarn. Sometimes people believe they are related to magmatic hydrothermal system. Some people don't believe that. They say, oh, unless you show me this intrusion, I don't believe it. But nowadays, there are more and more examples showing continuous transition from zinc lead to more proximal mineralization. And in China, the longest one is up to 4.15 kilometers, and zinc lead goes all the way back to the intrusion. So I think you can have more confidence that if you see zinc lead distal carbonate, either distal skarn or distal carbonate replacement deposits, you probably will have a proximal part related to that host, that zinc lead mineralization. And in fact, in China, the largest skarns, they all have their all parts discovered. That means the intrusion, inside the intrusion mineralization has been found, proximal mineralization, all the way to distal mineralization, or even to carbonate replacement mineralization. When you find the whole system, you will get a large tonnage, and you will see those. And so it's encouraging to follow up with those distal copper zinc lead. It's more traditional, but you also know now there's also distal copper or distal moly and distal gold deposits. Okay, I may take this advantage and use half a minute to advertise about our professional master's degree in mineral exploration at Colorado School of Mines. It's focused on mineral exploration. It's coursework only, no thesis. Requires 30 credits from coursework, so roughly about 10 courses. If you are really keen and you can finish 5 courses per semester, it can be finished in 2 semesters. So 9 months, you get this degree. And if you need to go back to work, we have also certificates as steps towards the degree. You finish 4 courses, you get 1 certificate. You get another, maybe 2 years later, 1 year later, you come back for another semester, you do another certificate, then additional 2 courses, then you get a degree. No GRE requirement, so the hard part of the English test, we can waive that. And the courses, we have organized that into block mode, similar to the professional master degree in Australia. And theoretically, you don't need to leave your job to do this, but we're in the United States and the visa is a problem. So far, if you are in America or probably in Canada, you probably can do this too. And you don't need to leave your job. You just come to take 1 course, finish 1, and come back for another course, and you accumulate 10 courses, you get a degree. And it's mostly for industry career. Okay, thank you very much. I'm sorry I'm over time. Yeah.
It's okay. Thank you very much, Zhaoshan. That was really interesting, really clear, and a really nice overview. So thanks for that. And so yes, so Zhaoshan, I think you can leave your screen up for the discussion.
Yeah.
And with that, Aaron, do we have any question?
Absolutely. Thanks so much, Zhaoshan, for that. I mean, very thorough overview of skarn systems with some of the cool features that you can see in the field, all the way to the detailed laboratory analysis. It's really great. And I think we have a lot of questions coming in on YouTube and here in Zoom as well. One of the questions that's come in from both sides is actually about one of these lesser seen features, or these features that aren't always seen, these fluid escape structures. And so I'm going to unmute Emma here on Zoom, and we can go ahead and have the first question.
Yes, hi. That was a very good presentation. Thank you for that one. So, yeah, regarding my question, yeah. So in the field, or in the core, how do you really differentiate stylolites from fluidscape structures? Because we're seeing this stylolite. We initially thought that it's stylolite, but seeing your picture of the fluidscape structure, now I'm confused if that is stylolite or fluidscape structure.
Yeah, stellarite is the term for the sedimentology. But if you see that shape of veins and you open the veins, use your hammer, open the veins, and if you kind of red color or black color, maybe iron or manganese sites, or even you can still see the disseminated pyrite in those veins, and this will be good.
Okay, thank you for that. And can I have one more question?
Sure. Yeah, sure.
Yeah, because several years ago, one of my first jobs, I'm working on a gold mine, but it's actually in an area of gold and porphyry copper. And then we hit this beautiful section of garnet, epidote, hematite, and specularite, and I think that was wollastonite, and it was my first time to see that skarn. Or and then one of our consultants said that it actually belongs to a retrograde skarn. So can you like give me an idea on how that works as well and how that
Yeah.
fits in? Yeah.
Yeah, so today we are talking about zoning patterns, which is space
Mm-hmm.
concept, and the TAM concept is the paragenesis, and we didn't, so we didn't have time to talk about that. But in general, scars always form form high temperature to low temperature in several stages, and the earliest stage, the progress stage, will form garnet, pyroxene, wollastonite, and those are the progress stage. And
Mm-hmm.
then the temperature goes down, we have retrograde alteration, and relatively early temperature, higher temperature, early retrograde alteration, the assemblage is typically epidote, amphibole, magnetite, sometimes hematite, sometimes muscatavite, which is the magnetite pseudomorphine specular hematite or specularite. And then you go going further down, and you start to have sulfides together with chlorite, quartz, and calcite. And the last stage is the barren calcite. You always have a bit of barren quartz vein, calcite vein cutting across everything. So that's the typical stage. And the mineralization always occurs in the retrograde stage. In the high temperature stage, we have done fluid inclusion analysis. And if you look up economic geology, zinc lead scar. The first author is Qihai Shu, is one of my PhD students, and second author is me. And if you look at Baiyin Nor, and it has very detailed single fluid inclusion analysis. High temperature pyroxene, the zinc lead is weak percent, but they don't deplete out because temperature is high, salinity is high. So zinc lead transported by chlorine, so they have high salinity, they don't deplete out. Until the temperature is lower, the metal will always come out at lower temperature because the lower temperature plus mixing with groundwater, you reduce the solubility of the metals dramatically, and then you get a combination of those metals deplete out. So that's mostly, almost all the scars have this kind of pattern. The mineralization came in, well, not really came in, it depleted out from the fluid in the retrograde stage. Iron is relatively higher temperature, so maybe 500 to 400 degrees C, and then sulfides, copper is earlier than zinc lead, and gold typically occurs together with bismuth and tellurium minerals, and they are even later than zinc and lead, that kind of pattern.
Yes, thank you. Great. Thank you very much.
Thank you.
So the next question is about distal fluids. It's on YouTube from Ilham Ilmawan. He's asking if could the fluid escaping the structure be found in volcanic calcareous wall rock, not in marble? And he's wondering what is the boundary between the fluid escaping and the whole rock, and also if there is any alteration halos.
Yeah, so far the fluid escape structures we look at is mostly calcite veins. So if it is closer, we're having a project at Candelaria in Chile, and closer to the intrusion, the veins can be much wider, or close to the ore body, it's much wider, and then you go out, the veins getting narrower and narrower, eventually to be those very narrow veins. And the inside, so the mineralogy typically is calcite. In volcanic rocks, I'm not sure if you have a scar, have some limestone on the pathway, you may get the calcium, and you may have a little bit of those veins, but probably not as abundant as in carbonate area. We haven't done much work in there. It's just my guessing. And by that time, the temperature is really, really low. So it may or may not have much visible alteration. When you have really low temperature, your alteration change from like the cerussite change from muscovite to elite, then to elite smectite, interlayer mineral, and eventually in some epithermal low sulfidation, intermediate sulfidation epithermal, it becomes smectite, like montmorillonite, which is the swelling clay. Maybe you will get that kind of smectite. And then by that time, sometimes it's getting difficult to say if this weathering product smectite or alteration. But if you have tiny bit of sulfide together with the smectite, then you can be confident that those are alteration happen, not just weathering. And for that, you will need a TIMA or TerraSpec to do that kind of detection.
Thanks.
Sorry, did I answer all your question? I remember you have more.
I think that was clear.
Yeah, I think it's just a good question of like, what are we looking for when these fluid escape structures cross from the marble outside of that lithology? Like, and I think you answered that pretty clearly. At least what we would expect to see is good. We have tons of questions, but I think what I want to do is I want to actually ask my own, because we can transfer it. We can talk about one of the things that I think is the most important from what you talked about, and that's the influence of oxidation state and this sort of classification that you described as sort of the premise of the talk. And so I'll just start with this question: is like, oxidation state of the magma seems to control the metal availability for the skarn systems that form adjacent to them. But there is also this influence of the host rock on controlling the metal deposition, right? So are we missing some deposits somewhere where metals aren't able to be deposited even though they are available? And maybe
yeah, if you look at the skarns are good, because if you have carbonate wall rock, carbonate is very reactive. So carbonate, if you have, say, chlorine complex metals like zinc, lead, copper, tin, when they depositate out, they generate a little bit of acid. And if you have carbonate to buffer the acid, it actually helps the mineralization. And so that's why there's lots of even high sulfidation, Cerapasca, Corcahilca, they are hosted in limestones. And you look at the alteration front, there's carbonate hosted massive zinc lead mineralization. So as long as you are in mineralization in carbonate, it will probably make you deposit most of your metals. On the other hand, you want to have examples of metals in the fluid but deposit out, then you need to go to look at the porphyry environment in the volcanic rocks. And I'm sure you have seen lots of fluid inclusion, single fluid inclusion analysis of porphyry deposits. And many of them, people are only talking about copper and gold. But if you look at the metal, the zinc lead typically is at weight % level. And you don't have porphyry zinc lead mineralization. That's because you actually don't have that kind of pH buffer offered by the carbonate. So in porphyry deposit, the zinc lead actually get dispersed in more distal halo rather than ore bodies.
Right. I guess, yeah, that makes sense, because the ongoing buffering by the carbonate, even though you're no longer growing necessarily calcsilicate skarn, you're still buffering the system with the carbonate that's being dissolved there, right? And precipitating.
That's right. Okay. Yeah. Volcanic rocks can buffer the acidity by forming cerussite, but that capacity of buffering is silicates are not easy to dissolve or alter compared with carbonates. So they're relatively slow. That's why it gets dispersed. If it deposits slowly, therefore it gets dispersed. It doesn't form a concentrated body. True.
So along these lines of oxidation, reducing, and metal content, I'm going to ask a question for Bonnie Broman, who says that we're working on a peak gold's the the peak gold skarn deposit in Alaska. It has 10 million tons at 4 grams per ton gold and 0.15% copper associated with actinolite and extensive pyrrhotite. No obvious causative intrusion. Where does this fit in this model?
Yeah, that's pyrrhotite is an indication of reduced environment. If you are in the field or even with lab work or photography, if you see the most reducing material, you probably will see organic carbon, probably most reducing. Then you go to native carbon, which would be graphite. That's also reducing. Then the sulfide would be lolingite. If you see lolingite, that's really reducing. And then after that is pyrite and pyrrhotite. That's a reducing condition. Then you go to more oxidizing condition will be magnetite together with, sometimes it can occur together with pyrite. Then you go to hematite, is more oxidizing condition. So those mineralogy, and you can use in the field to tell the redox state. And if you see lots of gold, not much copper, and of pyrrhotite, I would say that's a fairly reduced environment. And you also need to look at your wall rock. If your wall rock is very dark color or black color, then you can't tell whether the source is oxidized or reduced. It could be an oxidized source, but locally at your local condition, because your local rock is so reducing, and then it can reduce everything to pyrrhotite. And if your wall rock is just light gray color or even white color, but you have lots of pyrrhotite, then source must be reducing. And if you go that pathway, you probably find more gold along that, getting closer.
Thanks. On the frame of the oxidation states, we have a question from Jair. You're unmuted almost. No. He was wondering if you could track proximal and distal zone by using magnetite content in your skarn.
Yeah, like I just mentioned, the mineralogy, you see magnetite, that's already a moderate oxide condition. And if you start to see either muscatavite or hematite, it means there either currently there was oxide condition, more oxide condition. If you see pyrrhotite, that's more reduced condition. And if you see lolingite, that's even more reduced.
Okay. Sorry for that. Aaron, I think you have an anonymous question, maybe.
Yeah, sticking with this this idea of the oxidation state being one of the determining factors. We have an anonymous question about the Taylor skarn system that was discovered in Arizona, and it actually has a huge manganese silver ore body. And are there any other examples of these ore bodies, which would be distal, well, very distal, I presume. And is it a skarn ore system, or how can it relate to a skarn ore system to have manganese silver? Yeah,
silver, Uchuchacua in Peru, that's a distal skarn to carbonate replacement, and it's zinc, then go to lead, and then go to silver, then go to manganese. So you have that zoning pattern. And I think 2018, when I visited there, a few holes is start to see copper and definitely narrow decks of causative intrusion. There's skarn zoning patterns of skarn pointing toward that narrow deck, and with also skarn in the deck. And it's just the deck, maybe only a small hypothesis out of the major intrusion, but they continue to look for the system, and they're starting to see the more proximal part. And yeah, Uchuchacua, there's a lot of silver also.
Nice. No, Aaron, you want to go ahead? Or otherwise, I think we have a question from Marcelo Imania.
Yeah, if Marcelo wants to be ask his question directly, that would be awesome.
Yeah.
Hey, hello, good afternoon.
Hello.
Good afternoon.
Yes, I was just interested to know if in your experience, are there skarns that can be formed at very shallow conditions? I mean, economic skarns that can be formed at very shallow conditions, like in the epithermal environment. I know from Larry Maynard that, for instance, we can form calc-silicates in the active volcanic environment.
Yeah, the shallow ones will follow the distal ones, the zinc-lead ones, and their progress stage, they can be down to just 380 to 400 degrees. It's relatively distal and shallower, but you can't be really too shallow. If you go too shallow, so there's the structural geology, they will tell you if your pressure is higher than 1/3 of the tensile strength or something, and then your fracture will keep propagating, and then until it reaches the surface. And in that case, you lose all of volatiles, and it's not good for your mineralization. It has to be a certain depth, not too deep. Well, for skarns, it can be deeper than porphyry. Porphyry, if you do the calculation or look at the calculation in Burnham 1997 or earlier, it typically depends on your initial water. If your initial water is about 3%, your maximum depth is 4 to 5 kilometers. Otherwise, you just don't have enough water to break out the magma chamber. Skarns can be deeper because there's CO2 increasing the water solubility. So the deposits will have a depth range. It can't be too shallow, it can't be too deep. If you go further deep, you form pegmatite deposits. The water doesn't come out of the magma chamber, you form pegmatite deposits and don't form porphyry or skarns.
Thank you.
Thanks, Zhaoshan. I'm going to get a question in from YouTube from Rogerio Cavalcante. He asks, Professor Chang, what are your probable hypotheses on the origins of tungsten in the tungsten skarns?
Sorry, hypothesis tungsten, what part of tungsten?
Sorry, on your hypothesis for the source of tungsten.
Yeah. Yeah, the tungsten comes out of, again, from intrusion from the magma. And well, watch out for this. I have a student just finished watershed in Queensland. It's actually, it's metamorphic hydrothermal fluid. So in some of them can be related to magma. Occasionally, you may have ones related to metamorphic fluid, like the organic gold system. The reason for that is tungsten transported as hydroxyl and water complexes. So they are not related to chlorine. So they don't need chlorine. So they can be versatile. And so many organic gold deposits contains various amount of scheelite. But watershed may be an extreme example that it contains a lot of scheelite but no gold. That's the only metal actually can be probably related to metamorphic hydrothermal rather than magmatic. Most of them.
You say that normally it's from these highly fractionated or these fractionated melts that are producing the tungsten.
Yeah, the melt itself, the melt is highly fractionated. That's one thing. But in terms of redox, it can be more reduced. It can be more oxidized. So it's not picky in terms of redox, because no matter is oxidized or oxidized or reduced, tungsten can't go into any igneous minerals. So they will be concentrated in the residual melt anyway.
Right. No, thanks. Marion, is there another question on YouTube? Or
Yeah, we have a next question, maybe from someone who found olivine in skarns, but Arton Pasquier Castillo is wondering if we can actually find olivine in skarns, Zhaoshan.
Find evidence in scars about what?
Find olivine, sorry, not evidence.
Oh, olivine in scars. Yes, that's called magnesium scars, and I did my bachelor degree on magnesium scars. So if your wall rock is dolomite, then you end up with a magnesium scar. The early stage they form olivine. It can be magnesium-rich olivine phosphorite, and it can be also calcium magnesium olivine monticelite. And then you can also have magnesium-rich pyroxene, which is diapside, and definitely very little iron, not much iron, and only a little bit of garnet, not much garnet. And then even before the hydrothermal elevation, you can already start to form periclase, which is magnesium oxide in the dolomite, dolomitic limestone. I mean marble, dolomitic marble. If you have impurities in the marble, in the dolomite, and then those olivine and pyroxene will retrograde to chondrodite and another mineral, and then eventually altered to phlogopite, and eventually to serpentine, and a little bit of chlorite, maybe a little of brucite, and talc. So typically, it's a current day. It's like the ultramafic rock. The olivine is very easy to retrograde. So in the current day, you mostly are looking at a lot of serpentine, and yeah, and sometimes some researchers get confused and they say, "Oh, there's lots of serpentine. It must have been an ultramafic rock, and it was mapped as ultramafic rock." And you need to watch out for this. If you have dolomite wall rocks and you think about the possibility of being actually a magnesium scar, way to tell the difference between whether it's wall rock, whether it's magnesium scar or it was magnesium scar or ultramafic rock, you look at the magnetite. Look at the titanium content. Hydrothermal magnetite in scars, the titanium content is less than 1%. And if it is related to a magma, and that would be magmatic magnetite, it will have high titanium vanadium content. And yeah, and if you still see olivine and magmatic ultramafic rock, the olivine is a solid solution between phosphorite and phaeite, which is magnesium and iron end member. And it's very difficult for them to go to magnesium phosphorite more than 90%, because that really requires high temperature. The melting temperature would be more than 1500 degrees Celsius. And but for skarns, it's very easy to get pure phosphorite. And so that's another thing. If you see olivine and you look at the combination, it's almost pure phosphorite, and the likelihood of being a magnesium skarn is relatively high. So there's a few evidence you can look around and make a judgment.
Thanks, Zhaoshan. Yeah, actually, a couple of weeks ago, Marion and I were actually hiking in the Swiss Alps and found a rock associated with an old arsenic deposit, but the rock was mostly diopside and serpentine. So actually that brings up another question: is do magnesium skarns have different metal associations than what you described here today with the calcic skarns?
And there's I think worldwide there's magnesium copper, but not in China. There's most of the metal related to magnesium skarn is iron, and that's because if the magma release iron and the iron doesn't go into those silicate minerals, and they just deposit out as oxides. So everything the same. The magnesium iron skarn will have more iron than the calcic skarn equivalent. There's gold skarns in magnesium skarns, and there's moly in magnesium skarns. Copper a few, and yeah, if you look at my paper in the special population, you will see a more detailed documentation of that. Right now, a few things are a little bit vague in my mind.
Yeah, we'll be sure to check that out. That's a great special publication issue.
Zhaoshan, how do you feel? We are past 15 minutes now. Are you okay to keep going and answering a few more questions, or are you tired?
I'm fine. I'm happy to answer questions. Yeah.
So we have a different question from Mark Peterson. I will ask it for him. Would or could the marble conglomerate texture shown in your example from the Philippines be an example of fluid release structures that have been filled with clay?
Those clay, actually, it looks like clay. It's actually, if you, it has been changed to reaction skarns. The thing is, you can tell is, the way to tell reaction skarns is in the field, you look at something, it's brownish color, it just looks like clay, but it stick out of the ground, higher, slightly, maybe half centimeter higher than your marble around it. And if you see that, you need to use your scriber to test the hardness. If it is, I bet it's hard. Because it's resisted weathering. And because it's hard, you know it's actually changed to calc-silicate hornfels. In that case, that particular photo, most of them has changed to yellow, light yellow color garnet, and with a little bit of pyroxene, with a little bit of epidote. So they are no longer, they are actually already reaction skarns. It's getting fairly close to the major hydrothermal skarn body. And again, I mentioned metamorphic skarn a few times. So watch out for this, because in the paragenesis, so an intrusion comes out before the water is released out of the magma chamber. You already have heat, and you have thermal metamorphic metamorphism, and that will change calcareous shale to hornfels, and that's without any involvement of water. So that's a metamorphic process. And at the boundary between limestone and clay, and you can form those reaction skarns. That's again also a metamorphic skarn before you have those massive hydrothermal skarn. So that's the context of this. Obviously, if the same process applies to regional metamorphism, so you can have kind of very large scale, widespread reaction skarn or calc-silicate hornfels. In fact, some of those form lots of wollastonite, and it has been mined for wollastonite as industry minerals in Canada, in Japan, and in China. There's some of those are metamorphic skarns. No water involved for industry minerals.
Oh, thanks, Zhaoshan. We've had a lot of questions about sort of formation categories, styles, mechanisms. But we actually have a question on YouTube about exploration, which I think we should go ahead and ask, because it's quite important, and it's the whole reason. I think it's the foundation of why we research skarn deposits. But HJT Bar asks, given that you have figured out this alteration, zonation, and lithology distribution, where is the best to drill? He says there's not really soil geochemistry data, but there's ubiquitous magnetite. Basically, now that we know this alteration profile, where can you recommend drilling to explore once you, to explore?
Yeah, it depends on the metal you expect. If you are expecting to have zinc lead, and you probably want to drill close to the marble front, or even inside the marble or limestone, because that's getting into the carbonate replacement, and those are zinc lead are distal. And if you are expecting moly, and you're drilling very close to the intrusion and even inside the intrusion. And if you are expecting copper, then copper will probably be your skarn zone 1/3 from your intrusion. That's probably you have your peak of copper grade. Because getting close is temperature too high, getting away temperature too low, and that's Bingham or Carl and that's the example where the highest grade is about 1/3. You still have copper next to the intrusion proximal, but the highest grade is about 1/3 of the zoning pattern.
Yeah, it's actually an interesting question. The skarn deposit I work on for my PhD is actually, in the sense of its prograde skarn mineralogy, is actually monomineralic. There's no garnet, and rhodonite is a manganese-rich pyroxene skarn.
Yeah. Yes.
With rhodonite appearing only at the very edge. So 98% of the skarn is johanssonite, but we don't have this mineralogical zonation, and identifying the chemical or isotopic zonation is a lot more challenging. Likewise, we don't have a causative intrusion. So, which is why I'm studying it.
If you are in a small area, you may see the whole system can be, the trackable system can be 4.5 kilometers long. And there's even more distal zinc lead skarns where no intrusion has been found yet. Maybe some people are thinking 10 kilometers long. So in that kind of scale, if you depends on how large area you're looking at. If you're looking at an area of say 500 meters by 500 meters, and that's actually a small part of a big system, and the trend is showing up in the larger scale. If you're only looking at a small part, that probably within that small part, it doesn't show much.
Yeah, the Madan ore field in southern Bulgaria is actually about 15 square kilometers big, and none of the deposits there have any significant amount of garnet. They're all lead zinc or lead zinc silver skarns. And one of the thoughts is then that mineralization continues down. It's deeper instead of laterally extensive. So this is
definitely a possibility, and especially if there are faults, and lots of examples, the distal zinc lead mineralization occurs along major faults where is the fluid conduit.
Yeah, this is what we see. This is what we see with mineralization being transported by veins. But I will stop hogging the time. I think Marion has some questions to ask from our chat.
It's actually a question from Miguel Gaspar. Who is unmuted.
Hello, Zhaoshan, how are you?
Hello. Yeah.
Well, I've been listening to this talk while I'm driving, so I stopped the car to actually ask you a question, because this is we've been working on skarns for a long time, and one of the things that always puzzles me is you have these metasmatic fronts with this massive garnet, massive pyroxene, massive in the metasmatic front you have this volastonite. How do you think is the replacement process? Because you can transform, and I'm thinking about several different skarns like Crown Jewel, where you have these metasmatic fronts. They basically you have garnet skarns replacing either marble or volcanics. So how do you see this mechanism of, is this a dissolution reprecipitation thing? Because you have this massive replacement for one mineral that has the same composition, no matter which protolith you are.
Yeah, I agree with you because in the massive scar, the original bedding texture has been or obliterated, and
Yep.
no longer have that bedding, and so that's indicate probably the whole limestone has been maybe dissolved bit by bit, and you dissolve something and you precipitate something, and
Yeah, because in a lot of these things, in a lot of these systems, the rocks, the protolith itself, it's very massive. It's not porous, so you have to create space for the fluids to migrate, right? So you have to dissolve and reprecipitate, and that's why it's the dissolution fronts, which are metasmatic fronts, are so sharp. Because you are having reactions, dissolution reprecipitation reactions occurring along the fluid pathway.
Yes, yeah, I totally agree with you. And then depends on the protolith. If it is relatively package of limestone, maybe dirty limestone, you get this total dissolution. And actually, during if it is dirty limestone during the thermal metamorphic stage, you form the clay and the calcite already form reaction score, or maybe just grains of garnet or pyroxene. And that actually, when you form those, you already release some CO2, and you actually create a secondary permeability. And
Yep.
the fluid to get into the limestone even more. So that's why probably sometimes they better than the massive pure chemical precipitation limestones, where the calcite are interlocking and very low permeability.
Yep.
And where if you have sometimes if you have interbedded limestone and shale, and then those ones actually can develop into bonded skarns. And
yes.
Yeah, and then it keep some parts of those original bedding texture left.
Yeah, because if you have interbedded protolith with different permeability, you're gonna have fluids migrating at different rates, at different dissolution rates, and so you actually might see some zone skarns related with the bedding, but sometimes all those things are obliterated. It depends on the reactivity plus permeability of the strata.
Yeah, then the amount of hydrothermal fluid, if you get
yes
fluid source, there's a flood of water, and then no matter how hard the rock, and eventually it's broken.
Actually, I would like to add one thing about banded skarn systems. When you get this mineralogical alteration, repetition, it's not just the lithology of your host rock, but actually there can be these self-organizing structures in which you reach a boundary layer condition and you start to crystallize a new mineral. What do you think about these as a mechanism for forming banded skarn?
Yeah,
this would be like the work of Guy in the 80s and the Russian in the 70s before him.
Yeah, the word self-organizing, that's kind of a myth to me. It's like philosophical, but I always like to see the details and exactly what's the mechanism of doing that. And sometimes I don't see those details. It's just a concept.
But for example, if you have a very thin laminated politic Semitic sequence, and you have a fluid that is charged with sulfur, you're gonna have in the politic layers, you're gonna have deposition of arsenopyrite, which then is a geochemical trap for gold, for example. And so sometimes the gold is not on the marble layers or in the more sandstone layers, but it's more on the more reduced layers where the sulfides deposit. And sometimes you have these layered sulfide, non-sulfide, sulfide, non-sulfide, and the gold is always together with the sulfides.
No, that's
Yeah.
true. In terms of silicates, though, I've seen this in Yarrington with like on the centimeter scale, you can
Yes.
get garnet, pyroxene, garnet, pyroxene, garnet, pyroxene.
Yeah, and when I did my master, I study a layered sequence, and when you have the protolith that is enriched in aluminum, you have garnets, and when you have a layer that is enriched in silica and magnesium, you have pyroxene. So you have this interbedded, either sometimes clinosite, actinolite, very fine centimeter, millimeter, or garnet pyroxene.
Yeah, I think
But in that case, in that case, what happens, in my opinion, is that the system is buffered by the rock, not by the fluid. Because when it's buffered by the fluid, everything is obliterated. If
That's right.
the fluid rock ratio is very high, you're gonna have everything obliterated.
That's right. Yeah, I totally agree. Yeah.
It depends on the fluid rock ratio.
Yeah, I think I like this. To be honest, this discussion here at the end is really great to have Miguel, to have you on and Zhaoshan at the same time.
Yeah, I just stopped the car to do this discussion.
That is real dedication.
Thanks. That's good. Yeah. Take care. And the same thing. Sometimes the major composition difference, like there's also a scenario. They are both limestone, but one layer of limestone is white color, one layer is black, one layer alternating the white and black limestone, and the black one is more organic carbon or more reduced, and you end up with more pyroxene. Yeah, another way, or
yes, it depends on the oxidation state of iron, basically.
Yeah, I like this. I'm still entertaining for now the idea of this self-organized chemistry resulting from fluid dynamics, but I think you're right. It's very specific cases where this can happen, and I don't know if most banded skarn deposits are from this. I just wanted to throw that out there as
the fluid dynamics and self-organization is actually related with different diffusion rates of elements within the same fluid.
Sure, it requires a more stagnant fluid, right? So that the fluid has time to basically
equilibrate with the Ostra.
So, no, thank you both so much. Actually, it is 8 o'clock here, and it is time for us to wrap it up. Miguel and Zhaoshan, thank you so much for this discussion here at the end.